energy, how we generate energy, how we transmit energy, and how we use energy efficiently. This week we've had COP26, big discussions on climate change. Energy and how we use energy is a very important part of our journey towards a greener society. Towards net zero. Today, greenhouse gases from transport in the UK, transport's contribution to greenhouse gases, about 34% of carbon emissions is due to transport, automotive, trains, airplanes. Over 70% of the fuel used in industry today is from fossil fuels. There is a different way. There is a better way. Wind, solar, tidal. These sources of energy, much greener. How do we use those sources of energy, and how do we transmit those sources of energy to us, and how we can use that in our everyday lives? For example, wind energy, turning those blades, that mechanical energy is then converted into electrical energy. And then that electrical energy is transmitted to us with the power grid. We see this in our homes with the mains at 240 volts. Power electronics is a technology that enables us to convert electrical energy from a certain voltage to another voltage. This conversion, and doing this efficiently, is incredibly important. And what do I mean by that word, efficiently? The power that goes into our power electronics device, a charger or an inverter or a converter, we want the same power to come out of that device, 100% efficient. On this journey that we have towards net zero, let me take us back a bit to 1947. The discovery of the transistor. Probably one of the most important discoveries of the 20th century. The transistor can be used to amplify or switch electric currents and electric signals. That ability to use the transistor to convert and switch electric currents enables us to go from certain voltages to other voltages and currents and frequencies if we're looking at alternating current using power electronics. And today, in power electronics, we are moving away from silicon as the semiconductor material towards new materials such as silicon carbide or gallium nitride, other semiconductor materials, but they are more efficient in converting energy, power, electrical power from one voltage to another. There has been another significant trend in the electronics industry over the last 50 years. Let us go back to 1965. In 1965, Gordon Moore, the co-founder of Intel, wrote a paper, and in that paper he stated that the number of transistors on a piece of silicon would double every 1 year to 2 years. In 1975, the number of transistors on a piece of silicon, i.e. the chips in your mobile phones or laptops, was 65,000 transistors. Today, the number is in the billions. These transistors are now down at the nanometer scale, a few atoms wide. But what has that enabled us to do today? It has enabled us to analyze and process massive amounts of data very quickly, i.e. what you do in your mobile phones. So we've seen this tremendous revolution in digital technologies and the tech industry. Moore's law for data processing and power electronics for converting energy efficiently. So, the transistor, the integrated circuit, these being assembled with other electronic components onto printed circuit boards or substrates that make up a inverter that could be in an electric car. These all come together. They could be semiconductor materials there. There is metals for the electrical currents to flow around our product. There's also plastics that could be in this product, i.e. your mobile phone or laptop. Each of these materials has different properties, and in particular, they have what is known as the coefficient of thermal expansion. Now we know, you pick up your laptop and sometimes the fans are whizzing around, it's getting hot. And when it does that, each of these materials all want to expand by a different amount. The plastics want to expand by a certain amount. The semiconductor chip is trying to expand by a different amount. And the metal tracks and the other materials in there, all at different amounts. These expansions due to heat creates what's called stress, mechanical stress. So every time you're switching on the device and switching off the device, you're getting these expansion and contractions occurring. That leads to a phenomenon known as fatigue. The materials would degrade over time. And after 5 or 10 years of heavy use of a mobile phone, it will probably start to stop working due to material degradation and fatigue. Continually switching off and switching on. So, for the design engineer at companies like Apple and Microsoft and Samsung, it's very important to ensure that the actual design of these circuit boards are optimized in terms of the way those materials behave and interact with each other as you switch these on and off and as they get hot and cool. Now, that's the area of electronics packaging. Let's come back to Moore's law and what Moore's law has enabled us to achieve today in terms of massive amounts of data analysis and simulations. It has enabled us to be able to predict the way a converter in a car, changing one voltage to another, the way that that would behave before you actually built this converter in real life. So for example, we can use digital design tools today to optimize the layout of the electronics in a power converter, and also the placement of the semiconductors and the transistors in that to ensure that they will behave good thermally and also to ensure they meet the reliability requirements for the product that's being designed. So for a mobile phone, we'd like to ensure that that would last at least 5 years. For an electric vehicle, the power electronics in that, we want to ensure that that lasts for at least 15 years. If we had the electronics in an aircraft reliability would be at least 25 years. Now, these technologies, the digital design technologies, being able to predict electromagnetic fields, being able to predict temperature and stress and the way materials behave at the early design stage for, say, our mobile phone, before you actually built the mobile phone. Again, very, very important. What we're also seeing today is the capabilities of analysing tremendous amounts of data using AI and machine learning. So the ability to predict the physics that takes place in our mobile and also combine that with the latest advances in AI and machine learning is enabling us now as design engineers to move towards what we call the digital twins. Every product around us will be digitized. It will have a digital twin that we can then use to optimize the design of that product and its performance. So, we're on a journey. The journey to net zero. With regards the generation of clean energy, renewable energies, the move away from fossil fuels as an energy source. Electrification will be the key thing here. Power electronics to use to enable the conversion of electric power from certain voltages and currents to other voltages and currents that we would use in our products. Doing that with the latest advances in power electronics so that the conversion of energy from one form of a voltage to another is done efficiently. These are strong trends that we're seeing today. But in designing the next generation of power electronics and inverters, for example, for electric vehicles, we're using the power that Moore's law has given us in terms of the compute power and the capabilities that we have to use simulations and modeling tools in the design process to simulate the behavior of our devices before we actually build them. And this is providing tremendous insight into how to lay out electronic products and optimize them in terms of reliability. So we're on this journey to net zero, and electrification is the key thing here, and generally it's now time to turn that dial to full electrification. Thank you.